Ions, charged atoms, are at the heart of every IonQ quantum computer. They have many properties that make them ideal quantum bits, or qubits. Unlike manufactured qubits, ions are naturally quantum. Their stable and precise atomic states are perfect for high-quality computation. We use laser pulses to change the state of our ion qubits. We can flip from a 0 to a 1, or even create a superposition of both. We use a different laser to read out the final state of our qubit. In one state, the ion emits light. In the other, it stays dark. Adding more qubits is easy. Because each one is perfectly identical, they all behave exactly the same. When we have many qubits in a linear chain, we can use our lasers to perform operations on any two qubits on demand. Unlike certain quantum computers that have fixed layouts or need to move qubits around so they can interact, each ion in the IonQ computer can talk directly to every other one without moving. This allows us to more efficiently express the full power of the qubits in the chain as a computational system. The ions are held in place by an ion trap chip, an array of microfabricated electrodes that interact with the ion's positive charge to keep them perfectly still. Each trap can fit many qubits. The limit to how many qubits we can add to a single chain is not physical but practical. As we add more ions, the chain becomes more sensitive and harder to control. But we have a way around this. We create multiple cores made of smaller groups of ions. The intricate electrode patterns possible with microfabricated trap chips enable the precise control required for multi-core operation. In the future, we plan to create multiple gate zones, allowing for parallel operations in multiple cores. Additionally, we are currently limited to a handful of cores in a single line, but our trap R&D efforts are working towards adding many more and perfecting the ability to move and recombine them at will. Advanced chip design, qubit transport technology, and laser control technology are key enablers for our future vision of a multidimensional grid of cores, each individually controllable and reconfigurable. In addition to greater qubit density, they also pave the way for error correction, potentially allowing for many logical qubits connected in a single ion trap. While we increase the capacity of each quantum processing unit, or QPU, we also plan to overcome our other two great challenges to scale, making each system smaller, more integrated, and more manufacturable, and connecting these units together with photonics. First, we'll discuss integration and miniaturization. The control electronics, laser and detection optics, vacuum chamber, and more are currently many separate subcomponents, optimized for fast R&D iteration, not for producing hundreds of units per year. In the coming years, we plan to condense and combine many subsystems, reducing our overall footprint, enabling manufacturability, and allowing us to customize each component for ideal performance. Chips will become integrated packages with built-in photonics, laser routing, and detection. Control electronics will be condensed and refined, and the vacuum chamber at the core of our current generations will be replaced with a robust, integrated vacuum package, greatly reducing the overall device footprint. Not only do miniaturization and integration drive production costs down and enable commercially relevant scale, it also makes the system better, more stable, with more robust quantum control and more options for moving quantum information within and between each module. Once these units are compact and integrated enough, we may be able to put one or even multiple into a single standard server rack. Simultaneously, we'll be working on networking multiple quantum systems using photonics and fiber optics, enabling potentially limitless scale. Each additional QPU can be fully connected with all other units thanks to a software-controlled optical cross-connection switch. This means that we can directly connect any qubit with any other qubit throughout the entire system, providing enormous gains in runtime efficiency. Executing on these plans gives IonQ the potential to be the first to market with a truly commercial-scale quantum computer, and in the process, unlock quantum computing's world-changing promise.